Hello, gals and guys. Mr. Ambrose here. Hope everyone had a good weekend. So I'm going to be doing another video here, but it's not going to be a trig video. And so you might be wondering what we're going to do next. So as you might have guessed, we're going to be looking at probability next. Like my other videos, if you want to print out the lesson for today, it's on Classroom and you can take notes as I go through an introduction to probability for today. So in the beginning here, we have a spinner, and you'll notice that there are 5 numbers here. And if we were to perhaps spin that around, take a spinner and just spin it around, we want to determine what's the probability of getting an even number, which here we didn't. As with your work perhaps with probability in the past, the probability of getting an even number, hopefully you'd agree that since they are the even numbers 2 and 4, that probability would be 2 out of the total number of numbers that we have there, which is 5. And then find the probability of not spinning an even number, denoted by P of not even. Well, that would be the remaining numbers 1, 3, and 5. So there are 3 of those numbers out of the total number of 5. And that's just a simple probability of getting those 2 events there. So when you're dealing with probability, there's some terminology that you should perhaps be familiar with. So an experiment is any happening whose result is uncertain. And so like the spinning of our wheel, that could be considered an experiment because when we spin it, we don't know, what the result will be. The possible results of the experiment are the outcomes. So in our spinning of the wheel, that would be the numbers 1 or 2, 3, all those numbers would be considered outcomes. The set of all possible outcomes of the experiment is a sample space. So in our spinning of the wheel, all the outcomes, 1, 2, 3, 4, and 5, that would be considered our sample space. And then any subcollection of a sample space is an event. So the subcollection in our example would have perhaps been getting an even number. That would be considered an event of our experiment of spinning our wheel. So with that terminology in mind, we can define rigorously, I guess, or somewhat rigorously, definition of probability. And so the probability of getting an event E, not just even, but just an event E, is given by the ratio, the probability of getting that event E will equal this N of E, where N of E is all the outcomes that fall into the event E. So in our event of getting an even number, that number would be 2 because there were 2 even numbers on our spinner. And then that's over N of S, which represents the number of outcomes that fall into the entire sample space. In our spinning of the wheel, right, that total number of outcomes was 5. And so with that definition, now we'll consider, well, between what 2 numbers must all probabilities lie? And I claim that the lowest number that you can get would be 0. The lowest probability you get would be 0, because if we have perhaps, or consider an event, the lowest number that you can get of events would be 0. You can't get anything less than that. And 0 over any non-zero number is 0. But then the highest number that you get, I claim, would be 1, because even if the event perhaps includes every single value, every single outcome in the sample space, that's the greatest that can be. So the greatest that this number in the event value could be would be the same as this value here. And so we know that any number divided by itself is 1. That's the greatest that we could have as a probability. All right, so let's take a look at the first example in this lesson. We want to consider the spinner shown below, and we see that it has been divided into eight equally sized sectors of a circle. And the spinner is spun once. In the experiment, we will let A be the event of it landing on an even number, and B be the event of it landing on a prime number. And what we're instructed to do here is actually just to fill in our Venn diagram with the actual numbers from the spinner. Now, you perhaps have had some experience with filling in a Venn diagram, and so we can start doing that. But I just want to remind you guys that when you do fill in numbers into a Venn diagram with respective events, you do have to be careful. So, as perhaps an example, here's a Venn diagram with 3 different possible events, more than what you'll deal with in this class. And when you have possible outcomes, such as like here in this example here, we have new parents. When you go to place that outcome in your Venn diagram, you do want to be careful where you place it, because while new parents, because they have young kids and babies may be up all night, they're probably going to be awake all night, so you'd want to consider them in as part of the circle here. But also perhaps because they're up all night, they might have black circles around their eyes as well. So when we place this outcome in our Venn diagram, we have to make sure that we place in the right spot. If we place new parents over here, that would mean that they are awake up all night, but they wouldn't have black circles around their eyes, which is probably going to be the case for a lot of new parents. So with that in mind, as we perhaps try to place these outcomes in our Venn diagram, we can do it one at a time, just keeping in mind, where we should place these numbers, these outcomes. So the number 1, well, 1 is not an even number, so it should not be in this circle here. But careful, 1 actually isn't a prime number either, so it can't go in this circle here. But since 1 is a part of our sample space, so it's part of that, I'm going to put 1 right over here because it's not even, it's not prime, but it is part of our overall sample space. The number 2, well, the number 2 is even, so it definitely should be inside the circle. But interestingly enough, 2 is also a prime number, so 2 has to be placed right over here because it is both even and prime. And then from there, 3, well, it's not even, but it is a prime number, so I'll put 3 there. 4 is even, but not a prime, so I'll put 4 there. 5 is not even, but it's a prime, so I'll put 5 in that circle. 6, it's not a prime, but it is even, so I'll put 6 over here. 7 is not even, but it's a prime, so I'll put 7 there. And lastly, 8 is not a prime, but it is even, and so I'll put that number there. And so now we have our Venn diagram properly drawn out for this particular problem. All right, so now that we've looked at an example where we filled out a Venn diagram, let's consider another term, or some few other terms. A set is a collection of things that satisfy a well-defined criteria. And when we have 2 or more sets, we can talk about their union and their intersection. So the union of 2 events is defined as, well, if we have the events A and B, and X is perhaps an element. If X is in A or it's in B, then X is considered a part of the union of the sets A or B. And in our Venn diagram, that would represent basically any number that is found anywhere inside the 2 circles that make up the 2 sets. So that's how we define union. Terminology-wise, we use the word or to represent the union of the sets A or B. And symbol-wise, you see this little symbol here, which almost looks like a U, that you sometimes see to represent the union of the sets A or B. The intersection of 2 sets, terminology-wise there, we use the term N to represent the intersection of A and B. And symbol-wise, you see this symbol here, which almost looks like an N to represent the intersection of A and B. And the intersection of 2 sets is such that X has to be in A and B at the same time. So in our Venn diagram, the element 2 was in the intersection because it is right in here. It's in both sets A and B at the same time. So it's those elements that are in that part of our Venn diagram. So referring back to our prior example, if we now list out the set of numbers in the union of the 2 sets A and B, the union of the set of numbers that are both even and prime, well, that would represent all the numbers 2, 3, 4, 5, 6, 7, and 8. And so that would be these numbers here. So I'll list those out. 2, 3, 4, 5, 6, and 7. That would be the union of the two sets that we just did in example 1. And the intersection of our two sets A and B, well, I said that that was just the number 2 because the number 2 was the only number that was in both sets at the same time. So now let's consider this equation here, which this stands for the number of elements in the union of our sets A or B. And does that equal the number of elements in just a set A plus the number of elements in just a set B? Well, if we again go back to our example 1, the number of elements in the union of our sets A and B, well, that's right here. And actually, sorry, I'm missing an element. So the number of elements in this union was 1, 2, 3, 4, 5, 6, 7. So there's actually 7 elements, 7 outcomes, I should say, in that union. Then the number of outcomes in just the number of even numbers, well, that's all the numbers just in this circle here. So that would be 1, 2, 3, 4 outcomes in our evens event. And then the number of outcomes in our event B is 1, 2, 3, 4 as well. And so if I put that now into our equation here, again, there were 4 even numbers and there were 4 prime numbers in each of those separate events. Unfortunately, hopefully you agree that this doesn't equal. And there's a reason why this doesn't equal and will not equal in most cases, because when I counted each of the number of outcomes in these events separately, what I did was I double counted one particular number. And the number I double counted was the number that was in the intersection of those two events, right? 2 was in the event A, but it also is in the event B. And so that got double counted. So what I have to do to properly account for the number of outcomes in the union of two sets is I can add up the two events separately that make up that union, but then we have to subtract out the number of events that are in the intersection of the two. Okay, so now let's look at another thing that you see in probability, and that's two-way frequency charts, which I believe you've seen a little bit from Algebra 1. And two-way frequency charts are perhaps another way to view sets and their union as well as their intersection. And so here in the example 2, we have a small high school surveyed 52 of its seniors about their plans after they graduate. They found the following data in the table and wanted to analyze it based on gender. So we see the number of students going to college are in this row. The number not going to college is in this row. And then the other, in this column here, we see the number of males and the number of females. And we see the totals of each of the rows and each of the columns. And notice that the whole kit and caboodle is the total number 52, which is the total number of seniors that we have. So abbreviation-wise for this problem, M is going to represent males, F will represent females, C is going to represent going to college, and N is going to represent not going to college. So based upon our table, we want to calculate the number of values that we have here. So this first one asks for what is the number of males in this problem. And here we see the column for males, and the total number of males is this value here, and that's 30. The number of females can be found right over here, so that's 22. The number of students going to college, well, again, this is the row for college, but the total number is right over here, so that's 29. The number of students not going to college, well, this is our not going to college row, and the total number is 23. Now, the number of students that are both male and going to college, well, that's going to be that value right here, because this is the row for number of males, and this is the column for males, and this is the row for going to college, and it's this value here that is the intersection of those two events. And so it's only 16 students that are male going to college. In a similar manner, the number of females that are also going to college is going to be this number right here, because this is our female event, this is our going to college event, and this is the intersection of two. That's 13. So now here we want to find the number of students that are in the union of the sets that are female and going to college. And we have to be careful because of what I mentioned right over here. This doesn't just equal the sum of these two events. We have to make sure to subtract out the number in their intersection. So the number of females, well, we said the number of females was 22. And we can add to that the number of students going to college. But we have to subtract out the number of students that are in the intersection of females going to college. And that was this value here, because remember, n represents the intersection. So we would have to subtract out that 13. And if we add those two up and subtract out 13, we get 38. Okay, so now let's continue with this problem and see this now connect to probabilities. In part B in this example 2, we want to determine what is the probability that a person picked at random would be a female who is going to college. Represent this as a union or an intersection. Now the verbiage here may not be so great, but if I were to say would be a female and is going to college, I hope that you would agree that this would represent an intersection. And so the probability of there being a female who's also going to college, well, that should equal the number of females who are also going to college. And in this problem, that was 13. And that should be over the total number of students that we have in the entire senior class, which was 52. And so this would be this particular probability. Part C, what is the probability that a person picked at random would be a female or someone going to college? Represent this as a union or intersection. And I hope because of the word or here, you would agree that this would be a union. So this should be the probability of there being a female or someone going to college. And so for this, right, we would find the total number of students that are in the union of the sets, female or college. And we actually just did that. That is 38. And then we put that over the total number of seniors, which is 52. Now in part D, we're asked to explain why the probability of the union of two sets is not going to equal the probability of the sum of the two individual sets. And so for this, well, we just calculated this probability, which is 38 over 52. The probability of there being females, well, the probability of there being females, where there are 22 females out of 52 total seniors, and the probability of someone going to college, well, there's 29 students going to college out of 52. And so clearly, I hope you would agree that these are not going to add up to just this alone. And the reason is the same reason to why the number of values in a union is not going to equal just the number that are in the values of the two sets separately. What we have to do here is we have to subtract out the amount that is in the intersection of the intersection of those two sets. And that's this particular probability here. And if we were actually to subtract this fraction from these two here, I hope that you would agree that that would equal the probability of the union of these two sets. So the general probability law for the probability of the union of two sets A or B is equal to the probability of A plus the probability of B minus the probability of the intersection of the sets A and B. And this is an important probability rule and law, whatever you want to call it, that you will see in probability and that you'll use throughout probably this year, and also if you go into statistics at some point in the future. So I hope this video helped remind you guys about certain things in probability that you've seen before, and also introduce a couple of new ideas. And please try to do the homework that was assigned for today. If you have any questions on that or anything in the video, please let me know. And as always, please take care and stay safe. And I will talk to you soon.